This video looks at the language and logic of proof, why, our QCAA subject matter, use implication, converse equivalence, negation, contrapositive, use the symbols for implication, equivalence and equality, use the quantifiers for all and there exists, use examples and counterexamples. Our skills in addition to use will be prove and express, and our success will be we'll be able to apply our knowledge to correctly complete the set questions. A quick review of the number system, which you saw in maths methods. Real numbers, or R, we're looking at the real number system at the moment. They can be split into rational numbers, or Q, and irrational numbers, I. We'll start with the irrational numbers first. An irrational number cannot be expressed as a ratio of two integers. Pi and E, our surds, which are square roots of non-perfect squares, and non-exact or recurrent decimals. Okay, so the decimals that have no sense, they keep going on forever. Looking at our rational numbers, or Q, rational number can be expressed as a ratio of two integers. They can be expressed as a fraction. They can be split into integers, our Z, or our non-integers. Non-integers, fractions, or exact decimals. Exact decimals can be terminating or recurring. Our integers can be split into negative integers, zero or positive integers, and positive integers can go down into natural numbers, n. Now, some textbooks believe that 0 is a natural number, so that is controversial, I suppose you could say. I have always done that 0 is not a natural number. So pause the video and think about what all these numbers are. Try and classify them. And pause, and then you can check your work. So 4.25 with the line above it means it's 4.25, and the 25 is recurring. So we know it's a recurring decimal. We also know that it is rational because it can be expressed as a fraction. Negative 0.35 is a terminating decimal, and it is rational because it can be expressed as a fraction. Square root of negative 16 is not real, so we have no classification for that. We cannot square root negative 16 in the real number system. Pi is irrational. 2.6 is a terminating decimal, so it is rational. Square root of 9 over 25 equals 3 over 5, so that is rational. If it was to be a decimal, it would be a terminating decimal. Negative 123 is rational, and it is an integer. 3 over 4 is rational, and if it was to be changed into a decimal, it would be terminating. Square root of 7 is irrational. 1.3 recurring is rational, and it's a recurring decimal. 1.35279045 keeps going. That is an irrational number. Okay, so we have no natural numbers here. Negating statements. To negate a statement, P, we write its very opposite, so not P. Okay, so negate the negative of it, the opposite of it. So if I've got the sky is green, that's a false statement. The negation of that would be the sky is not green, which would be true. 1 plus 1 equals 2, that's true. To negate that statement, we'd say 1 plus 1 doesn't equal 2, which would be false. All prime numbers are odd. That's false. There exists an even prime number is true. All triangles have 3 sides. True. To negate that statement, some triangle does not have 3 sides, which is false. So negation turns a true statement into a false statement, and a false statement into a true statement. So what I want you to do is pause the video and have a go at the following examples. Identify whether the first statement is true or false. Write the negation of each statement and determine if it is true or false. So 2 is greater than 1. That is true. The negation of that is that 2 is less than or equal to 1, and that would be false. 5 is divisible by 3 is false. The negation of that would be 5 is not divisible by 3. And that would be true. The sum of any two odd numbers is even would be true, and the negation of that would be the sum of any two odd numbers is odd, and that would be false. There are two primes whose product is 12. That would be false, and the negation would be there are no two primes whose product is 12. And that would be true. Now let's look at De Morgan's laws. Negating statements that involved and or require the use of De Morgan's laws. So not P and Q is the same as not P or not Q. And if you look at the Venn diagram, you can see what I mean by that. Not P and Q, well, P and Q is the blue. Okay, so not P and Q is all of the green. That's the same as saying not P or not Q. Okay, I know they're labelled as A and B here, but just for example, so you can see what that means. Okay, so if I'm looking at A intersects B, then the opposite of that, or not A intersects B, is the same as A, not A in union with not B. Okay, if I've got not P or Q, so looking at this diagram, not P or Q would be the green. Okay, so that's the same as saying not P and not Q. Okay, so if I want to write this another way, the negation of P and Q is not P or not Q. The negation of P or Q is not P and not Q. Okay, so when you've got and, the negation becomes or. When you've got or, the negation becomes and. So when we look at these two examples, negate the following statements. N is divisible by 2 or N is divisible by 3. Okay, so we would write N is not divisible by 2 and N is not divisible by 3. Okay, another way of writing that is N is divisible by neither 2 nor 3. Okay, x is greater than 0 and x is less than or equal to 5. The negation would be x is less than or equal to 0 or x is greater than 5. Okay, so you do the opposite of the statement and change the and to or the or to and. Okay. Looking at statements involving quantifiers, the universal quantifier, the upside down and, means for all. The existential qualifier, a backwards E, means there exists. Okay, So examples: translate the following statements into everyday language. Also determine whether or not each statement is true, justifying your answer. So for the first one here, upside down A means for all. So this says, or this means, so it asks put in everyday language, that the square of any real number is greater than or equal to 0. Okay? So if you think about that, the square of any real number is greater than or equal to 0. Well, that has to be a true statement, because if you square a number, it's going to become positive no matter what it is. Okay? So this is a true statement. As squaring a number even a negative number makes it positive. And also 0 squared is 0. Okay? Also 0 squared equals 0. Okay? Next one. We have the E, the backwards E, which means there exists. So this means that there is at least one integer, because it's dealing with Z, one integer such that the sum of the integers squared and twice the integer is prime. Okay? Is it a true statement? Well, 1 squared plus 2 times 1, so if n is 1, would be 1 plus 2, would be 1 plus 2, which equals 3. Okay? 3 is prime. Therefore, this is a true statement. You only need one example when you're talking about the existential quantifier. You just need one example that works. For all, you need to prove that it works for everything. So backwards E is a there exists. So this is saying there exists some n, which is a real number, such that x squared equals the square root of x. Okay? So this means that there is at least one real number whose square is equal to its square root. Okay, can we find an example? 1 squared equals the square root of 1, which equals 1. Therefore, this is a true statement. Again, you only need one example that works. Last one is a for all. So for all integers n, the number 5 times n is even. So this means that the product of any integer, okay, any integer and 5 results in an even number. Okay, so if I have let n equals 3, 3 times 5 is 15, that is not even. So therefore, this is a false statement because it needs to be true for everything. Okay, this is a false statement. So you have to remember that a universal quantifier has to be true for everything. So you can find one thing that doesn't work and you've proven it false. Examples and counterexamples. Providing a single example is always sufficient to prove that there is a there exists statement. Providing a single example is always sufficient to prove that a there exists statement is true, which is what I've just been saying. And providing a single counterexample is always sufficient to prove that a for all statement is false. Okay, so examples. Rewrite the following statements using the for all and there exists. Also determine whether or not each statement is true, justifying your answer. So the first one is the square root of any positive integer. So whenever you see that for any positive integer, you should be thinking that's for all. Okay, is less than or equal to the integer. So for all n such that it is an integer and it's a positive integer, okay, the square root of n has to be less than or equal to n. That's what that's saying. So let's think about it. N equals 1. The square root of 1 would be less than or equal to 1. So that's true. N equals 2. Square root of 2 has to be less than or equal to 2. So that's true. Now that would continue for n is equal to 1, 2, 3, 4. Keep going. We don't know what's going to happen for infinity, but we would assume that it is true. Okay? We would assume it is true. But note, we haven't proven it. Because we've only shown it for certain values. We haven't proven it. Let's look at the next one. There is at least one. So in this case, we're looking at the existence of a value. So there exists a real number that, when squared, results in a smaller number. Okay? So there exists n being a real number such that n squared has to be smaller than n. It has to be a smaller number. Okay, now we know that's not going to work for whole numbers because, say, 2 squared is 4, 4 is greater than 2. So let's look at fractions. So it doesn't work for whole numbers. What about fractions? Now note, it's the existence. There exists. We only need to find one example that works. So if I say, what if n is a quarter? 1 quarter, all squared, would be 1 over 16. And 1 over 16 is less than a quarter. So that works. So therefore, 1 over 4 all squared is less than 1 quarter. So I've shown the statement's true. I only need one single example. So therefore, this statement is true as shown by the existence of a single example. n equals a quarter. Okay, let's move on. Now note, order matters. For all and there exists can be used together in a single statement. However, the order in which they appear is important. Okay, so for all integers n, there exists an integer m such that m plus n is a multiple of 5. Now that's true. Okay, so for all integers n, there exists an integer m such that n plus m is a multiple of 5. We could find one single example of that. That is true. If I put it that there exists an integer n such that for all integers m, n plus m is a multiple of 5, that would be false because we need it to occur for everything. Okay? And that's not going to be the case. So negating statements involving quantifiers. The negation of for all statement is a there exists statement, and the negation of a there exists statement is a for all statement. So let's look at the examples. Determine the negation for each of the following statements. Also determine whether the original statement or the negation is true, justifying your answer. So I've got for all integers n, 2n is even. Okay, so that means that the negating statement would be there exists an n, which is an element of z, it's an integer, such that 2n is not even. Okay, so the first one was for all integers n, multiplying by 2 will result in an even number. It has to. It's a multiple of 2. Okay, so the original statement would be true, as a resulting number would be a multiple of 2. If we look at the negating statement, there exists a number which is an element, which is an integer, such that 2n is not even. That's false. If we multiply any number by 2, 2 is then a multiple, so it has to be even. Okay, so the original statement would be true, as the resulting number would have to be a multiple of 2. Okay, let's look at the next one. There exists a real number x such that x squared equals -1. Okay, hopefully in the back of your head saying, well, that's not true, because if we square anything, we get a positive. But anyway, the negating statement, we started with a there exists, so it's going to be for all x being a real number, x squared can't equal -1. Okay, we know that's true. The negation is true, is squaring any real number will either be 0 or a positive number. Okay, so the negation is true, as squaring any real number will result in either 0, if the number is 0, or a positive number. It can't be -1. Okay, let's move on. Conditional statements. So the statement, if it is raining, then the grass is wet. Okay, the conditional statement is if P is true, then Q is true. Or P implies Q, and we use that double arrow symbol. So P implies Q. P equals the hypothesis. Q is the conclusion. Now note not all conditional statements will be true. So if it is raining, then the grass is wet. That would be true. The grass would have to be wet. But if I put the grass is wet, if the grass is wet, then it is raining. Well, not necessarily. That's false. What if I use sprinklers? Okay? Or what if it rained before and the grass is wet but it's not raining now? Okay? So not all conditional statements will be true. Examples: rewrite the following conditional statements using the implication symbol. If n ends in a 0, where n is an element of z, so n is an integer, then n is even. So if n ends in 0, this implies that n is even. Okay? The next one, if n is greater than 3, is a sufficient condition to conclude that n is positive. So if n is greater than 3, this implies n is positive. It's very dodgy. You could also write that if n is greater than 3, this implies n is greater than 0. It's positive. If n is greater than 3 is necessary if n is greater than 4. So if n is greater than 4, this implies that n must also be greater than 3. Now let's look at the converse. The converse of a conditional statement is a statement obtained by swapping the statements on either side of the implication symbol. So the original, n is a multiple of 10, implies n is an even number. The converse of that would be n is an even number, which implies n is a multiple of 10. Okay, so for P implies Q, the converse is Q implies P. And you would note that in this case, the original n is a multiple of 10, n is an even number. That has to be true. But the converse, n is an even number, n is a multiple of 10, that is false. Okay, the contrapositive. The contrapositive of a conditional statement is a statement obtained by swapping the statements on either side of the implication symbol and also negating both statements. So the original, if is n is a multiple of 10, which implies n is an even number. The converse of that, that should say the contrapositive of that. Let me fix that. Make sure you fix your notes. Okay, so the contrapositive is n is not an even number, so we've swapped it over and done the negation there, which implies n is not a multiple of 10. So for P implies Q, the contrapositive is not Q implies not P. Okay, and make sure you do that correction. Now, the negation of a conditional statement. Original, if an animal is a poodle, then it is a dog. That's true. Negation, there exists some animal that is a poodle but is not a dog. First one's true, second one's false. So the negation of a conditional statement of the form P implies Q that involves some variable is there exists some value of the variable for which P is true but Q is false. Probably recommend pausing and just reading through that again so you make sure you understand what's going on. Let's look at some examples. Consider the following conditional statement. If n is a perfect square, then n is divisible by 3. Okay, if n is a perfect square, then n is divisible by 3. Change colour. So, part A, write the statement in the form P implies Q and determine if it is true or false. Okay? That would be for all n is a perfect square. And that implies n is divisible by 3. Okay, if n is a perfect square, then n is divisible by 3. So for all n is a perfect square, which implies n is divisible by 3. So let's look at whether it's true or false. A perfect square would be 1, 4, 9, 16, etc. Okay, it's a for all, so for all n, so we need one counterexample to prove that it's false. So let's think about a counterexample. If we look at 4 is a perfect square. But it isn't divisible by 3. Okay, I could also use 1, I could have also used 16. I just couldn't use 9. Okay, so therefore this statement is false. Okay, next, write the converse to the conditional statement and determine whether it is true or false. So the converse is going to be there exists n is divisible by 3, so we're swapping them over, which implies n is a perfect square. So the converse, we just swap it across. So let's look at that. It's a for all, so again we need one counterexample. So multiples of 3. 3, 6, 9, 12, etc. Okay? So one counterexample that proves this is false. Let's look at 6. 6 is divisible by 3. So it makes, that's the first bit, it's divisible by 3. But it isn't a perfect square. Okay, so being divisible by 3 doesn't imply that it's a perfect square. So therefore, the converse statement is false. Let's look at the next one. Write the contrapositive to the conditional statement and determine it is true or false. Okay, so that's for all n. This is the same as the converse, but the opposite, the negation. So for all n is not divisible by 3, which implies that n is not a perfect square. Okay, so let's look at what we've got. So not divisible by 3. So we could have 1, 4, 2 would be good, wouldn't it? 1, 2, 4, 5, 7, 8, etc. So they're numbers that aren't divisible by 3. It's a for all, so we only need one counterexample. So counterexample, 4 is not divisible by 3. But it is a perfect square. Okay, so in this case, therefore, the contrapositive is false. D, write the negation. So write the negation to the conditional statement and determine it is true or false. So the negation, the conditional statement was a for all, so the negation is going to be a there exists. There exists n such that n is a perfect square. But is not divisible by 3. Okay, so perfect squares. We've got 1, 4, 9, 16, 25, etc. Okay, example. Let's pick one. 4 is a perfect square. And is not divisible by 3. Okay, we only need one example that works, so therefore the negation is true. Okay, last lot. Logical equivalent statements. Recall, our original n is a multiple of 10, which implies n is an even number. That is true. The converse of that was n is an even number, which implies n is a multiple of 10. That was false. Okay? So using like sometimes a conditional statement and its converse, though, can both be true. Okay? So original, x is equal to 5 and 2x equals 10. That's true. The converse, 2x equals 10 and x equals 5, that is true. So two statements are logically equivalent with if whenever one is true, the other must also be true. So this is where we have the double arrow. So you can go either way. Okay, implies forwards or backwards. So x equals 5 is logically equivalent to 2x equals 10. So I can read it both ways. 2x equals 10 implies x equals 5. So each of the following can be used to express the fact that P and Q are logically equivalent. P is necessary and sufficient for Q. P if and only if Q. And if and only if, you sometimes see written as IFF. P implies Q and Q implies P. Or P is logically equivalent to Q. So the example, rewrite the following statement using the logical equivalent symbol. For n to be divisible by 5, it is both necessary and sufficient that n end in either 0 or 5. Okay, so we've got n is divisible by 5. Our logical equivalent symbol, n ends in 0 or 5. Okay, so if n is divisible by 5, it has to end in 0 or 5. Or if n ends in 0 or 5, it has to be divisible by 5. Okay, probably this is one of those videos that you watch again. The exercise is exercise 3.2 from Pearson, so make sure you look in the Pearson section for the textbook exercise.